In episode 44, titled A/B Tests and Randomized Controlled Trials, Treatment Effects, Validity, and Common Pitfalls, we take the exam's causal questions and translate them into a simple mental model you can apply under pressure. When a scenario asks whether a change worked, the safest default is to imagine two comparable groups, one that gets the change and one that does not, and then ask what would be different if everything else stayed the same. That mental A/B framing keeps you from confusing coincidence with impact and keeps your language aligned with evidence rather than enthusiasm. It also forces you to think about how groups are formed, what outcomes matter, and what could go wrong, which is exactly what the exam is probing. The goal is not to memorize jargon, but to reason like someone who understands how credible conclusions are earned. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. At the heart of these designs is randomization, and its value is best understood as a defense against confounding rather than a fancy procedural detail. When you assign units, such as people, systems, accounts, stores, or regions, to groups by chance, you reduce systematic differences between groups that could otherwise explain outcome differences. The purpose is not to make the groups identical in every observable way, because any one random split will still show small differences, but to make the differences unrelated to treatment assignment on average. That balancing effect applies not just to variables you measured, but also to variables you did not measure, which is why randomization is such a powerful tool for causal inference. In exam terms, randomization is the mechanism that makes the control group a credible stand-in for what would have happened to the treated group in the absence of the intervention. With randomization in place, you can define what you are actually estimating, which is the treatment effect. A treatment effect is the outcome difference due to the intervention, meaning the change in results you attribute to receiving the treatment rather than to time, selection, or other background influences. It can be expressed as the average difference between groups after assignment, or as an average difference in changes, depending on the design and measurement approach, but the conceptual core is the same. The key exam skill is to separate the outcome itself from the effect, because a high or low outcome level does not automatically indicate anything about causation. In practice, you are asking, what is the expected difference in the outcome if we assign treatment versus if we assign control? And that counterfactual framing is what turns raw measurement into causal reasoning. A common point of confusion, and an exam favorite, is the difference between internal validity and external generalizability. Internal validity means the estimate is believable for the population and setting you actually tested, because assignment was fair, measurement was consistent, and bias was minimized. External generalizability means the result is likely to hold in other populations, other time periods, or other operational environments, which is a separate question that randomization alone does not automatically solve. You can have a perfectly internally valid test run on a narrow, atypical segment, and the effect might not translate to the broader environment where conditions differ. Conversely, you can have a broadly representative sample but flawed assignment or measurement that undermines internal validity, making any generalization meaningless. The exam often expects you to prioritize internal validity first, because a result that is not credible where it was measured cannot be safely exported anywhere else. Choosing metrics is where many tests succeed or fail, and the exam expects you to show you can design measurement that answers the causal question without creating avoidable ambiguity.
You typically need a primary outcome that reflects the main objective, such as reduced fraud loss, improved detection time, increased successful login security, or improved customer retention, depending on the scenario.
You also need guardrail metrics that detect harm, such as increased support tickets, degraded latency, reduced conversion, or increased operational load, because an intervention can win on one metric while creating unacceptable side effects elsewhere. Duration is part of metric design, because some outcomes respond quickly while others lag, and measuring too soon can miss delayed effects or misread short-term novelty as sustained impact.
The exam will reward answers that articulate how metric choice and duration align to the decision being made, rather than treating metrics as an afterthought.
Sample size is another area where practical intuition matters more than memorized formulas, and the exam tends to probe that intuition through trade-offs. The number of observations you need depends on the size of the effect you hope to detect and the amount of noise in the outcome, because small effects in noisy environments require more data to separate signal from randomness. If outcomes vary widely from unit to unit, you need more observations to average out that variability, while stable outcomes can reveal effects with fewer observations. This is why a test on rare security incidents often requires either a long duration or a higher volume proxy outcome, because the event rate is low and random variation dominates short windows. A good exam answer recognizes that more data is not a virtue by itself, but a response to effect size, variability, and the cost of making the wrong call. One of the easiest ways to ruin an otherwise sound experiment is to peak early and repeatedly, and it is a pitfall that shows up frequently in exam scenarios because it is so common in real organizations. If you check results every day and stop the test the moment you see a significant difference, you inflate the false positive risk because you are effectively running many tests and selecting the most favorable snapshot. Even if the true effect is zero, repeated looks at noisy data will occasionally produce a seemingly convincing gap, and stopping at that moment turns a random fluctuation into an official decision. The practical takeaway is that analysis plans should specify when you will evaluate results, how long you will run, and what stopping rules apply, so the probability of a false win is controlled. On the exam, the right instinct is to treat early peaking as a validity threat, not as a clever way to move faster. Attrition and non-compliance are also major threats, and they matter because they break the clean link between random assignment and actual exposure to treatment. Attrition occurs when units drop out of measurement, such as users who stop engaging, devices that stop reporting, or accounts that churn. And if attrition differs between groups, the remaining measured populations may no longer be comparable. Non-compliance occurs when assigned units do not follow assignment, such as control units that receive the feature anyway, or treated units that never actually receive it, which dilutes or biases the estimated effect. The exam may describe a scenario where rollout glitches, user opt-outs, or measurement gaps create asymmetric exposure, and the causal estimate becomes harder to interpret. A strong response acknowledges that these issues can bias results, and that you must decide whether the estimate reflects assignment impact, actual usage impact, or some mixture, depending on how the analysis is defined. Interference is a more subtle problem, but it is increasingly common in networked systems, and the exam uses it to test whether you understand independence assumptions. Interference occurs when one unit's outcome is influenced by another unit's treatment assignment, such as when users share information, attackers adapt, or controls change the environment for everyone. In security, One group receiving a new phishing warning might influence the behavior of colleagues in the control group through conversation, shared documentation, or copied settings, making groups less distinct than planned. In product contexts, social influence can cause adoption patterns to spill across groups, while in threat contexts, adversaries may respond to detection changes in ways that affect both groups. When interference is present, the naive difference between groups may understate or misstate the effect, and exam answers should recognize interference as a reason that experimental conclusions require careful design and interpretation. Stratification is a design tool that helps reduce chance imbalances in critical segments before assignment, and it is especially useful when certain segments are rare but highly influential. The idea is to separate units into strata based on important baseline variables such as region, platform type, account tier, or risk level, and then randomize within each stratum so each group receives a balanced share. This is not about forcing perfect equality, but about preventing an unlucky random split where, for example, one group ends up with most high-risk accounts and the other group gets mostly low-risk accounts. Stratification can improve precision and credibility, particularly when outcomes differ sharply across segments and those segments would otherwise create noise or bias. On the exam, choosing stratification signals that you understand randomization is powerful but not magical, and that design choices can strengthen results without undermining causal logic. Interpreting results responsibly requires both statistical and practical judgment, which is why confidence intervals and practical significance matter. A confidence interval expresses the range of effect sizes consistent with the observed data under the model assumptions, and it helps you avoid treating a single point estimate as if it were exact truth. Practical significance asks whether the effect, even if statistically convincing, is large enough to justify cost, risk, or operational disruption, because a tiny improvement can be real but not worth shipping. The exam often sets up a trap where a result is statistically significant but operationally trivial, or where a result is not statistically decisive but still suggests a potentially meaningful impact that requires more data or a refined test. A disciplined interpretation uses confidence intervals to communicate uncertainty and uses business or security context to interpret whether the plausible effect range supports action. Once you have a credible estimate, the next step is decision communication, and the exam expects you to connect evidence to action without overclaiming certainty. Sometimes the evidence supports shipping, meaning deploying the change broadly because the benefits are clear and guardrails look safe within the tested context. Sometimes the evidence supports iteration, meaning you have signals of benefit but also risks or segment differences that suggest refining the intervention or running a follow-up test with improved targeting. Sometimes the evidence supports rollback, meaning negative outcomes, guardrail failures, or validity threats indicate that continuing would be irresponsible. The key is that the decision should be justified by the measured outcomes, the uncertainty range, and the validity assessment, not by sunk cost or organizational momentum. On the exam, the best answers sound like accountable leadership, they tie a decision to what the test actually supports, and they acknowledge the remaining uncertainty. These designs fit into causal inference as the cleanest path to estimating treatment effects when you can implement them, but they also serve as a reference point for judging weaker methods. When randomization and controlled exposure are feasible, they directly support counterfactual reasoning because they create a credible what would have happened otherwise comparison by design. When randomization is not feasible, you can still use quasi-experimental approaches, but you should mentally compare their assumptions to the experimental ideal asking what replaces randomization and what new risks are introduced. The exam cares about this relationship because it is testing whether you understand why experiments are strong, not merely that they exist, and whether you can recognize when constraints force trade-offs. Thinking this way also prevents a common error, which is treating any measured improvement after a change as causal proof, when the real lesson is that design determines credibility. A useful anchor memory for these questions is simple: randomize, measure, avoid peaking, decide responsibly. Randomize reminds you that balancing confounders is the core engine of causal credibility, not a ceremonial step. Measure reminds you that outcomes and guardrails must be defined so the test answers the right question without hidden harm. Avoid peaking reminds you that process discipline protects you from false wins created by repeated looks at noise. Decide responsibly reminds you that the goal is not to get significance, but to make a defensible choice based on evidence strength, uncertainty, and the costs of error, which is exactly what the exam is asking you to demonstrate. To conclude episode 44, imagine a concrete test plan and then name its key risk, because that pairing shows you can design and critique a causal study rather than merely admire the concept. Suppose a company tests a new login friction step intended to reduce account takeover, so it randomly assigns a subset of users to receive the new step while others remain on the current flow. And it measures account takeover rate as the primary outcome, with support contacts and login abandonment as guardrail metrics over a duration long enough to capture normal cycles. Stratification could be used to balance high-value accounts and common device types across groups, and results would be interpreted using confidence intervals to judge both uncertainty and practical impact. A key risk in that plan might be interference, because users can influence each other through shared guidance and copied settings, or it might be attrition, because the new friction could change who continues to log in and therefore who remains measurable. The important exam habit is that every test plan should include both the logic for estimating a treatment effect and an explicit recognition of the most likely validity threat. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.